seminar, the first one in 2026. It's a great pleasure to introduce Professor Egon Schulte from Northeastern University at Boston, which recently experienced a serious snowstorm, but luckily everything is okay. So Egon will talk about local theory in Delone Sets and Tilings. Over to you, Egon, please.
Okay, thank you so much, Vitaly. First, I want to thank you particularly for inviting me to give a talk. It's 9 o'clock in Boston, so it's good morning. But for you, I guess for most of you, it's probably good afternoon or good evening, maybe even. So I'd like to talk about a topic that was introduced to me by Nikolai Dolbilin many years ago. And it's about the local theory in Delone Sets and Tilings. And I'd like to first phrase a general problem that's sort of underlying these questions about in the local theory, namely characterize global properties of a geometric object, I call it O, in terms of its local configuration, C of O. And if the local configurations, so we are looking for results like this, if the local configurations of O have properties A, B, C, say, then the entire object has properties X, Y, Z. And A, B, C are sort of pre-assigned for the class of object and the properties X, Y, Z as well. And specifically, we are interested in detecting transitivity properties of the symmetry group, G of O, locally. That means we want to sort of figure out locally why the whole object is extremely symmetric. And our objects here that we are looking at will be either tilings, it could be other structures like geometric complexes, abstract polytope, graphs, etc., and Delone sets also. These are the uniformly distributed discrete point sets in Euclidean space. I get back to them in a second. And the local configurations that we will be looking at can be different things, can be coronas for tilings, clusters for Delone sets, or more generally neighborhoods and vertex links, etc. So that's a general problem. Characterize global properties locally. And let me begin with tilings, because that's a little closer to my heart than Delone sets, because I'm sort of more a polyhedral guy. So the basic question, of course, in tiling theory is how can a space be tiled by copies of one or more shapes? And that's a very general question and has had a long history and it's of great relevance in mathematics in general, in particular geometry and geometry of numbers and applications in crystallography, in arts and other areas. And for us, we will always be talking about Euclidean space, Euclidean D space, ED. So the ordinary space would be the tree space and the high-dimensional analogs. And copies in our context can be different things. When I talk about copies, it could be translates of a given shape. They could be congruent copies of a given shape. They could be isomorphic polytopes. I will explain that later. And the shapes themselves can be very of different nature. It can be convex polytopes, can be non-convex polytopes. They don't have to be polytopes at all. They could be sort of topological objects which look like polytopes, topological polytopes, etc. And of course, perhaps one of the most familiar class of objects are the 5 parallelohedra in 3 space that already Fedorov classified. And these are the convex polyhedra that tile ordinary Euclidean 3 space by translations. That means you can take copies of these 5 polyhedra and actually tile space, and you can in fact tile in a unique face-to-face manner. So here are the 4 objects. So let me introduce some more terminology first. So for the purpose of this talk, a tiling T is a family of usually convex polytopes, or can be other shapes, but called the tiles of T, which cover ED without gaps and overlaps. And that is to say, every point lies in one of the tiles, and no two tiles have interior points in common. And it's an old theorem by Minkowski that if the tiles in a tiling are convex or compact, then in fact they must be convex polytopes. So convexity and compactness means convex polytopes. And all our tilings will be locally finite. So if every point in space has a neighborhood that meets only finitely many points, so we won't allow that the objects get too tiny, or that vertices accumulate to a point, or things like this. So everything is locally finite, well behaved. And tilings can or cannot have the property that they are face-to-face. So a tiling is called face-to-face if the intersection of any two tiles is either empty or is a face of each tile. So that means, for example, if you try to tile the Euclidean plane by squares, then the two squares actually have to meet along a common edge. And so face-to-face means that the intersection of any two tiles is a face of each tile. So it cannot happen that somehow the tiles are shifted relative to each other. The intersections must behave very cleanly. And here on the right you see a tessellation, actually face-to-face tessellation of space by truncated octahedra. Some more terminology. A tiling is a notion introduced by Grimholm and Shepard. I think they call it normal. So T is called normal if the tiles are uniformly bounded in size. So they cannot get too large or they cannot get too thin. So that's referred to as normality of a tiling. And we are particularly interested in tilings that are monohedral. That means where all the tiles are congruent to each other under isometries. So that can mean directly congruent or indirectly congruent. That means reflections allowed or not. So that's the class of object we are mainly interested in monohedral tilings. But we will also look at monotypic tilings. And that's a notion that's completely combinatorial. So in a monotypic tiling, the tiles are allowed to be combinatorially isomorphic. So it's no longer, for example, if I take a cube, say three-dimensional cube, then monotypicity means that the tiling by a cube as combinatorial prototile consists of polytopes that are combinatorially equivalent to the cube. So for example, they could be rectangular boxes, they could be parallelepipeds, they could even be neither of those, but still combinatorially equivalent. And what that simply means, that's a set of faces. So two polytopes are combinatorially equivalent if there is a bijection between the faces such that incidence is preserved by the projection in both directions. So monotypicity is a combinatorial notion for tilings with combinatorially isomorphic polytopes. In most cases, though, we will be talking about monohedral tilings. And one of the most fundamental questions in tiling theory is that of the space fillers in Euclidean D-space. And so the main problem is this: classify all convex D polytopes that admit a monohedral tiling of a D. So a space filler is a convex polytope that allows the tiling of space by congruent copies. And we can insist on the tiling being face-to-face, so no shifts relative to each other. Two tiles meet in a common face. And we could also insist that the tiling is isohedral, tile-transitive. That's a very strong condition. And the term isohedral was introduced by Grimholm and Shepard, and it just means tile-transitive under this symmetry group. And until relatively recently, even the planar case was not solved, but it has been solved just a few years ago. It had been known for a long time that all triangles and quadrangles tile the plane, and certain types of hexagons do as well. But the case of the pentagons had been open for a long time, and Manon has a definitive proof that there are only 15 types of pentagonal tiles, and each type is sort of has parameters attached to them. And so there are these 15 types of pentagonal tiling. So in the plane, the space filler problem or plane filler problem is solved. By the way, that's a general fact that if you have a normal tiling of a plane, so for example by a plane filler, then by n-gons, then this n can be at most 6. So you cannot tile the plane by congruent copies of a 7-gon or even uniformly bounded tiles with which are 7 gons. So basically we can, yeah?
Could I ask a question here?
Yeah.
So first, could you remind us what tile-transitive means?
Oh, yeah, good, thank you. Good, very good. Tile-transitive means, so we have a tiling of space, and tile-transitive means that if I have 2 tiles of the tiling, then I can find a symmetry of the tiling that maps the first tile to the second tile. Right? So
and the whole tiling
goes to itself. Yeah, would be, yeah, that's right. Right? So,
I see.
That's a very strong condition. Right? So for example, square tiling has this property in the square tiling you can move every tile to every tile, even by a translation. Right? But that normally it wouldn't be sufficient to just use translations. Right? So tile-transitive, the tile-transitive means that you can move every tile to every other tile by an isometry that preserves the entire tiling. So that is a symmetry of the entire tiling.
I see. Thank you, Egon. And could I ask also about quadrangles? So you say what all quadrangles can tile the whole plane.
Yeah,
right?
Yeah, that's right. That's a really fun thing actually. So the way to do this is if you have a quadrangle, even if it's not convex, then take any edge, take the midpoint of that edge, and take a half turn about that edge. Then you move the original quadrangle to another copy of the quadrangle, and the union of the two is a hexagon.
For a convex quadrangle?
No, for any.
No?
Yeah, for any quadrangle. And so you get a hexagon, and you can tile the plane by these hexagons.
Simply by translations?
Even by translations, yeah.
Yeah, for triangles, it's almost obvious you get a parallelogram, right, in this way.
Yeah, for quadrangles, it's not completely, it's just a very clever idea, I think. Right, so you attach a second copy of the hexagon along an edge, a suitable edge. And then you get a hexagon, and then you can tile. And that can be done for any quadrangle, yeah? So all triangles and quadrangles tile in certain hexagons. So basically the space filler problem is what are the analogs of the triangles, quadrangles, pentagons, and hexagons in D-space? And one way to approach this is to first look at the most symmetric tessellations in Euclidean D space. And everyone is familiar with the tessellation in the plane by triangles, hexagons, and squares. And in every dimension, you have a tiling of D space by cubes. In 3 space, that's clear, just the ordinary cubes, which are sort of attached along facets to each other. But there is a wonderful fact that in 4 dimensions, you have 2 additional tilings. And one is by 24 cells, and the other one is by 4 cross polytopes, hyperoctahedral. And what makes these tessellations regular is that they have not only tiles that are themselves sort of regular polyhedra or regular polytopes, but also their vertex structure, local vertex structure is the same everywhere and is regular. So one way to describe that in terms of the group is that the geometric symmetry group is transitive on the flags. And I need to say what a flag is. A flag is a maximal chain of mutually incident faces in the tiling. So a chain consisting of vertex that lies in an edge, that lies in the 2-phase, lies in the 3-phase, lies in the 4th-phase. And so if I have 2 different flags sort of in the tiling, then I find, again, an isometry that can map the first flag to the second flag and preserve the entire tiling. So that's the most you can have. And here is a 24 cell that I showed. That's a picture of the 24 cell. The 24 cell in 4 space has 24 octahedral facets. So the boundary is composed of 24 octahedra in a very symmetric fashion, and you can actually take, you can tile these space, 4 space by such 24 cells. And the picture here is sort of obtained in the same way in which the picture on the right is obtained for the 4 cube, right? So it's a projection of the 4 cube into 3 space on the right. And on the left, it's a projection of the entire 24 cell into 3 space. And because maybe I skipped this, but one can actually describe very neatly how the tessellations look like in 4 space. But in the interest of time, I think I better move on. Then I already mentioned tilings by translations. What happens if I only take a convex polytope and only allow translations of that convex polytope such that the entire space is tiled by copies of this original polytopes? So which convex polytopes tile ED by translations? And these are known as polyhedra, and it turns out there are only few in every dimension. And I already showed you the case D equals, oh, hold on, something is not, oh yeah, that's right. D equals 3. There are 5 such parallelohedra discovered by Fedorov. In the plane, there are actually just 2. And then it goes up, the number goes up tremendously. In 52, there are 52 in 4 dimensions. All these were already classified by Delone many years ago. And related to this question is this famous Voronoi conjecture, which says that every parallelohedron is an affine image of a Voronoi region of some lattice. And so here at the bottom you see sort of the notion of a Voronoi region depicted. There is a collection of points, and the Voronoi regions are just the points of space which are closer to a given point than to any other point. And this is the notion of Voronoi region, and if you have a lattice in space, then there are also Voronoi regions for that lattice. And the famous Voronoi conjecture says that every parallelohedron, so every convex polytope that tiles by translation is in fact affine image of a Voronoi region of a lattice. So it's a very strong statement, and it was proved for d less than or equal to 4 by Voronoi himself, and also for primitive parallelohedra. And now we also know the 5-dimensional case. And Alexey Garber proved this. I think Magazinov was also involved in the proof. That was just recently. And I believe Alexey is speaking in a seminar. I noticed that the other day. In a couple
yes, in February.
Yeah.
Egon, could I also ask a question about
sure.
counting with parallelohedra? So when we count with numbers 2, 5, 52, I guess we consider them up to some equivalence,
yes,
right?
Absolutely. So that's right. So it's affine equivalence. Affine, yeah. Think about it this way. If you have a tessellation of space, you can take an affine transformation of it, and that moves every tile to an affine copy of the original tile. So if you have a parallelohedron in 3 space and apply an affine transformation, it won't change anything. Right? So it's a very good question. So it's up to affine transformation.
Okay. So in the plane we have, I guess, parallelograms, which are all affinely equivalent.
Yeah.
And then what's it? Hexagons, but
hexagons,
I guess not arbitrary hexagons.
No. Centrally symmetric.
Centrally symmetric. Mm-hmm.
Yeah.
I see.
And then affine images of it.
Okay, thank you.
Good. So the whole field of tilings is very closely related to Hilbert's 18th problem. David Hilbert in 1900 had proposed a list of famous problems, and he has the 18th problem, and it reads as follows. There are 3 parts, strictly speaking. The first is, are there only finitely many crystallographic groups in ED? That was a question that he posed, and it turns out that the answer is yes. There are only finitely many crystallographic groups in every dimension. That was proved by Bieberbach in the 1920s. And so by crystallographic group, I mean a discrete group of isometries that have a compact fundamental domain. Then the second part that relates more directly to tilings, that's part B. Is there a polyhedral tile which admits a monohedral tiling but is not the fundamental region for a crystallographic group? And the answer is also yes. So a priori there is no direct connection between monohedral tileability, so to speak, and a group. Right? So in principle, there are monohedral tilings that do not occur as fundamental regions of something crystallographic. And that was proved by Reinhardt in 1928 and later by others, Hisch and Kirschner, Penrose also. And closely related to this is the following question. That lies pretty, it's very interesting from our perspective. Is there a polyhedral shape in space that admits a monohedral tiling, but not an isohedral tiling? So isohedral means, again, tile-transitive. So the question is basically, can you tile by congruent copies, but the whole thing is not tile-transitive? That's basically the question. And yes, the answer is there are so-called unisohedral tilings, and they were also discovered by Reinhardt and Hisch. And finally, there is what is the densest sphere packing in 3 space, and that was known as the Kepler conjecture and was proved by Hales that the Fermi I'm by accident. Are you still seeing me, or did something happen here? I lost.
Egon, yeah, if you could share the slides again, please.
I don't. What happened? Oh, for some reason we got. 1 second. I think I need to first go to this. Is the following problem, namely, so can one at least say there are finitely many combinatorial types of space fillers? Right. So it's clear that we had that if you have a hexagon and apply an affine transformation to it, we can move. So if you have a hexagon that tiles a plane, then the affine copy of it also tiles a plane. So that's basically the same kind of question. Are there only finitely many combinatorial types of space fillers? And there's a famous bound for the number of faces of a space filler in an isohedral face-to-face tiling. And so we have a convex polytope that tiles space, and in a face-to-face manner, but the entire tiling is isohedral, so it's tile-transitive. How many facets can such an object have? And that's an interesting and difficult question. And there was a proof by Delone and later a proof by Tarasov. It shows the number of facets is at most 2 to the d times h minus 1/2 minus 2, where h is the index of the translation subgroup in the full symmetry group of the tiling. And it is known from Bieberbach theorems that this index is bounded. So that provides us with a bound that only depends on the dimension. So the number of facets of a space filler is bounded if the space filler admits an isohedral tiling. And in 3 space, for example, you know that a space filler that admits an isohedral tiling can have at most 378 facets. And of course, that's it's pretty high. Let's put it like this, and it would be amazing if there was a space filler with 378. But we have, so how realistic is the number of facets? And there is still a world record by Peter Engel from 1980, and he proved that there are several isohedral space fillers in E3 with 38 facets. That in itself is an incredible result if you think about it. So you have a space filler with 38 facets admitting an isohedral space tiling. And if you look at the structure of that object, then the ratio of the area of the largest face to the smallest face is over 1 million. So it's an incredible object, really. But it has 38 face fillers, and that's still the record, I think. And recently there have been results by Borchis, I think that's the pronunciation, Sabariego and Santos from 2011, who showed that the Voronoi region for single crystallographic point orbits satisfies the number of facets at most 92. So if you have a crystallographic group, 1 point in space, and look at the orbit of that point and the Voronoi regions, then you can have at most 92 facets. But it's very likely that the number is actually a lot smaller. So that sort of describes the landscape of tilings and this local theory. And let me now describe the local theorem for monohedral tilings. And that's already due to Delone, Dolbilin, Stogren, and Garber in the 1970s. And what is the basic question here? So again, remember, monohedral means all the tiles are congruent. And so the question is, how can we detect tile transitivity, that means isohedrality, locally? So we want to only look at sort of the neighborhood of a tile and somehow detect that the whole tiling is tile transitive. That's a very strong condition. And the central notion, so we want a theorem of the following kind. A tiling is isohedral, that means tile transitive, if and only the local coronas, I explain what that is, behave in a certain way. And so let me begin with the notion of a centered corona. And here you see a picture in the plane of a tiling by triangles. And now focus on the tile P. Below is tile Q. But at the moment, focus only on P. Then the so-called first corona of tile P consists of all the tiles that meet this tile P. So it's a set of all triangles that meet this tile P, and that's a collection of all these dotted triangles. Right? So meeting can mean along an edge, can mean or along a vertex. Right? So the collection of dotted triangles is exactly the first corona. So it's somehow a notion of neighborhood. And if you look at this picture, you see that if you look at the first corona of Q, that's exactly the same first corona. So it can happen that two tiles have the same coronas. In most cases, that's not the case, but it can happen, which is why there is a notion of centered corona, which really sort of carries the tile along. So a centered case corona consists of the point of the tile P and the case corona, Ck of P, of a tile P, and that's defined as follows. So the zeroth corona is just the tile itself. The first corona consists of the tiles that meet the original tile, P, and non-empty intersection. The second corona consists of all tiles that meet a tile from the first corona, and so on. So Ck of P consists of all the tiles that meet a tile from the K minus first corona. So we take a tile, look at a corona, sort of as a neighborhood, first neighborhood, then we look at the corona of that, so to speak, and the second neighborhood, and so on. So we grow these coronas. And now we want to say that two coronas are basically the same in some sense. And that's a notion of pairwise congruence of two coronas. So we have a tile P and a tile Q. And along with them, the case coronas of P and the case corona of Q. And pairwise congruence of these two things means there exists an isometry that maps the first point to the second point and the corona, first corona to the second corona. And so that's, in other words, they are sort of equivalent on an isometry. Yeah, to case corona, centered case corona are equivalent if there's an isometry that takes the first to the second. There's also a corona group, namely the symmetry group of the entire corona. But symmetry group means in this case that also the center must go to the center, so to speak. I mean, so Sk of P is a symmetry group of the centered corona, consists of all isometries that map P to P, isometries gamma that map P to P, and the case corona of P to the case corona of, the case corona of P to the case corona of P and P to P. Right, so centers must go to centers. And it turns out that these symmetry groups cannot get larger, so as we grow the corona, so to speak, the symmetry groups get smaller and smaller. And it's, by the way, not enough to... so now the question is, how would one sort of describe this local theorem? So one idea would be to say we just focus on the coronas, and perhaps it's sufficient that the first coronas are equivalent, pairwise equivalent, but that's not the case. There are old examples by Peter Engel that show that it's not enough to look at first coronas only. There are pairwise congruence of first corona does not imply pairwise congruence of second coronas. So one has to be more careful here, and that's exactly happening with a local theorem for monohedral tilings due to, as I said, Delone, Dolbilin, Stogin, and Galiulin. So it says the tiling T is isohedral, that means tile-transitive, if there exists a K bigger than 0, such that any two centered case coronas are pairwise congruent, and the case corona group is the same as a K minus first corona group for all tiles. So in other words, the local theorem characterizes isohedrality in terms of pairwise congruence of the centered coronas, but also condition on the groups, on the symmetry groups. They have to stagger, so to speak. From then on, from that K on, they stay the same. And it turns out there's actually a universal bound for this K. It only depends on dimension D. So in K2, in the plane, it's 1 actually. In 3 space, it's 5, and that's related to this Delone-Tarasov bound for space fillers that I mentioned earlier. And so just to illustrate this theorem, here's an interesting case. Suppose you have a tiling you have a tile P that's asymmetric, right? It has no symmetries at all, except for the identity, right? So no actual symmetries. Then the theorem says that tiling is isohedral if and only if if K equals 1, that means any two centered first coronas are congruent. And the reason why that is sufficient is that these groups that show up in the second condition are all trivial, right? Because we assumed it's asymmetric, so they're trivial, so they come into, it's automatically satisfies the second condition, right? Only the first condition grips, so to speak. There's also a notion, there's also a local theorem for, let's look at the time, 1 second. There's also a local theorem for combinatorial tile-transitivity. And that's sort of the question here is, I will skip most of this now, because time is already quite advanced. The question is, which convex D-polytopes admit a monotypic tiling by convex polytopes that are all combinatorially isomorphic to P? So for example, in the plane you're asking the question, suppose I'm asking the question, can you tile the plane with 7 guns? We know that can't be done in a normal way, sort of it cannot be congruent or anything like this, or even uniformly bounded, but it is possible. You can actually file tilings in the plane by convex heptagons. And in fact, you can even pre-assign how many meet at a vertex. So that would be, the tiling would be an example of a monotypic tilings. Any two polygons with the same number of vertices are equivalent, combinatorially equivalent. There's the same way in which the incidence occurs between vertices and edges. And again, you can ask questions of face-to-face and combinatorial tile transitivity, and there's a whole interesting background here also. But I just want to point out that there's also a local theorem for monotypic tilings that Nikolai Dolbilin and I discovered a couple of years ago. And now the question is, how do you detect combinatorial tile transitivity? So you are no longer allowed to use isometries, or you are allowed to use isometries, but that's not all what you're allowed to use. So combinatorial isomorphisms, or the entire tiling. And there's this local theorem which says T is combinatorially tile transitive if there exists an integer k, such that any two centers case corona complex is isomorphic, and the combinatorial automorphism groups of the case corona complex is the same as that of the k minus first corona complex. So the theorem on the surface looks exactly the same, but it's actually a very different theorem. In the monohedral case that we discussed before, you had isometries on the ambient space that provided sort of these pairwise congruence notion. So there was a space, and the isometries of the space made everything happen. That you don't have here. It's a combinatorial object in some sense. So, and what you need to do here is the local isomorphisms that occur between coronas, they need to be extended to global isomorphisms of the tiling, and that can be done sort of along paths. So, and simply connectedness plays a big role. But in any case, so there is a local theorem. The proof is very different from the original theorem. Okay, let's talk about Delone sets. And Delone sets are mathematical models of crystals and used heavily there for modeling purposes. And what is a Delone set? It's a uniformly distributed set, a point set in Euclidean space. And Delone sets come with two parameters, little r and capital R. And we denote them by capital X. And the defining properties are every open ball in a D of radius little r contains at most one point of the set. A better way almost to say this is any 2 points of X have a distance of at least 2 times little r. So the minimum interpoint distance is at least 2r. So that defines the parameter little r. Now the capital R. The condition is every closed ball in a D of radius capital R contains at least one point. So if I have a big ball of radius r, capital R, there's at least one point in it, in the closed ball. So in other words, R is the radius of the largest empty open ball, so to speak. Right? So if you go smaller, if you take a ball of smaller radius, then it can be empty, right? But if you go to R, then this property is satisfied. So, So the question is, how can we characterize Delone sets that are so-called regular systems? And we are using here the sort of an old definition of Fedorov, namely that a Delone set is called an ideal crystal if its symmetry group S of X has finitely many orbits on the Delone set. So in other words, the Delone set is a union of finitely many orbits under the symmetry group. And the most interesting case for us was that of the regular systems, special type of Delone sets, or regular point sets. And the Delone set X is called a regular system if its symmetry group acts transitively on X. So a regular system is just a point orbit under a crystallographic group. And the ideal crystals in the sense of Fedorov are the unions of finitely many regular systems. So we will be focusing on regular systems. The basic question is, how can we tell from the local data of a Delone set that it is actually a regular system? Right? So how does the transitivity surface? And we proceed in a similar way as in the case for the tiling, for monohedral tilings. And we look at the Delone set locally. So we introduce a notion of a row cluster, so to speak, a row corona, if you want, a row cluster at a point X of the Delone set. So clusters are only defined at points of the Delone set itself. Namely, Cx row consists of all the points of X that are at distance at most rho from X. So in other words, X intersected with a ball of radius rho about X. Right? So the cluster captures everything of the set at distance at most rho from the center, from X. And as I said, these are centered clusters, so X is sort of distinguished as a center. And the parameters show up now. Namely, the clusters are full dimensional if rho is at least 2 times this capital R. Right? We had this, for Delone sets, we had these 2 parameters, little r and this capital R. And the clusters are full dimensional if we have a radius at least of 2 times r. And clusters can have a nice symmetry group, namely, and we call it the cluster group or local symmetry group. And it's a stabilizer of a point X in the full symmetry group of the cluster. So in other words, we look at all the symmetries of the cluster, but we look at only those that also fix the center. So that it's sort of the center keeps its role as a center under symmetries. Then we need a notion of equivalence. What does it mean that 2 clusters are equivalent? So we had 2 row clusters at points X and X prime. So Cx row and Cx prime row are said to be equivalent if there's an isometry sigma of the ambient space that maps the whole cluster Cx row to Cx prime row, but also the center X to X prime. Yeah, so if we have 2 patches of this Delone set, which are clusters, then equivalence just means that they're congruent, but that also the congruence that takes the first to the second maps the center to the center. That's what equivalence means. Yeah, congruence plus center to center. And then it is true that for every regular system, any 2 such row clusters of X are equivalent, right? Because if you have transitivity of the Delone set, on the Delone set, if the symmetry acts transitively on the Delone set, then it also takes row clusters at a point to row clusters at another point. So the transitivity provides that the row clusters are automatically equivalent. But we are now interested in the opposite. Namely, can we sort of detect the regularity of a system just by looking at clusters? Right? That's what we want to study, and that's a local theorem for Delone sets due to again to Delone, Dolbilin, Stoger, and Galyulin. And that explains sort of the emergence of the crystallographic group of symmetries for a Delone set. That means that the Delone set becomes the orbit under a crystallographic group. And the theorem says that the Delone set is a regular system, so it's an orbit under a crystallographic group. If there exists a radius rho naught, such that any two rho naught plus 2 are clusters of X are equivalent, and the cluster groups stabilize exactly at that radius. That means Sx of rho naught is Xx of rho naught plus 2r. So in other words, we want equivalence of clusters of big enough size and also stabilization of the symmetry groups of the clusters at that point. And one interesting question is, what can we say if we only focus on the clusters themselves, only on the equivalence of two clusters, and sort of drop the conditions on the cluster groups in the theorem? And that leads to the notion of the regularity radius. And so the question is this: we want to find small numbers rho, so small radii rho, such that each Delone set with equivalent rho clusters is a regular point set. Right? And there, of course, can be many rows, and in fact, there's a smallest such row. And what that smallest such row gives you, and that's not clear that it exists, but it does, it's called rho d hat. And it's characterized by two properties, namely each Delone set with equivalent rho d hat clusters is regular. That follows directly from the definition and the fact that there exists the smallest one. But also that it's really the smallest one, namely for all radii smaller than this rho d hat, there exists a Delone set with equivalent rho clusters, which is not a regular system. So you do not, in other words, there is no such rho below this regularity radius that has the desired property that equivalence of the rho clusters implies regular system. And we have been studying this rho d hat, the regularity radius, and there's an upper bound for the regularity radius in work by Dolbilin, Lagarius, and Senechal some 25 plus years ago. And if you look at this rho d hat is at most 2r times d squared plus 1 times the 2 logarithm of 2r or 2 capital R over little r plus 2. And the first term here in this product is nicely behaving, but the second term has a ratio capital R over R. And that can be huge in a Delone set. So what one would want to know stronger results, only dependence on maybe capital R and the dimension. And there were some results by Nikolai Dolbilin already and Stogerin, and the first real breakthrough came in work by Baburin, Bunyaev, Dolbilin, Eric Horvitz, Garber, Krivovichev, and myself. 2017, it's more than half of a soccer team, so to speak, so a lot of people. And we had a workshop at the American Institute of Mathematics in California. And one of the outcomes was that we were able to establish a lower bound, a linear lower bound. Namely, this rho d hat is greater than or equal to 2d times capital R. And for 3 dimension, it shows that rho 3 hat is at least 6r. So it's not sufficient to just take, say, in 3 dimensions, coronas of type 4, to look at coronas of radius 5r, say. You need to go to coronas at least of size 6R to guarantee that equivalence of these coronas implies that the whole thing is regular. And it's a pretty clever construction that actually underlies this theorem. And I think I need to move a little quicker because we're getting to the end. So we have this nice lower bound for rho d hat for the regularity radius, a linear lower bound 2dr. And in 3 dimensions, so one is obviously interested in upper bounds. And in 3 dimensions, we have a concrete upper bound, and that was proved by Dolbilin, Garber, Leopold, and myself, namely that rho 3 hat is at most 10R. Most credit actually goes to Nikolai here for proving this, but it's, the completion of the proof is in this joint paper. And it also has an interesting proof. So what you really use here is the fact that these cluster groups are finite subgroups of O3. Finite are finite isometry groups. And finite isometry groups in 3 dimensions are known. There's essentially a finite list. And one can sort of knock down some groups that cannot occur as these cluster groups. And for other groups, you can actually prove that that you automatically have regularity. And so that's how the proof proceeds. And now I can leave you with some conjectures to prove. We have some conjectures in a recent paper by Nikolai Dolbilin, Garber, then myself and Marjorie Senechal, just from 2025. And I can offer 2 conjectures, and the second one implies the first. So a weak conjecture and a strong conjecture. And the first conjecture, the weak conjecture, says that the regularity radius is O of d squared log d times r. That means rho d hat is less than or equal to constant times d squared times log d times r. Right? So and that's not so bad if you think about that the lower array the lower bound is already 2dr. So it has linearity. But here you have basically a quadratic bound, log d having a minor rho. But then there's a second conjecture that actually says, and I believe that's probably the actual truth, that's my guess, namely that rho d hat is actually OD log d times r. So rho d hat is less than or equal to constant times d times log d times r. And so in other words, if the second is true, then we are very close, then the lower bound is very close to the upper bound in terms of asymptotic behavior. And we have evidence for these proof, for these conjectures, for particular types of Delone sets, for example, Delone sets, where the points of minimum distance from a given point are full dimensional. They satisfy this even with OD squared times R, or sort of reachability in, that's a technical thing. It's maybe too complicated to explain now. But we have a second class where we can actually sort of prove that that the first conjecture is true. And finally, some evidence for the strong conjecture, OD log d times r, comes from another question. That's the so-called group, we call that the group order problem. Namely, bound the size of the 2R cluster groups, SXR, in a 2R isometric Delone set. So we are looking at Delone sets where the 2R clusters are all equivalent. And then the 2R cluster groups Sx2r do not depend on the particular point x where you are. They're all isomorphic for different points, they're isomorphic. We're interested in the size. And we have a concrete conjecture, the group order conjecture, that says the cluster groups of radius 2r are bounded always. They may by 2 to the d times d factorial. And that's the order of the symmetry group of the cube, 2 to the d times d factorial, or cross polytope, or hyperoctahedral. And it can be shown that the group order conjecture really implies that the regularity radius is O of d log d times r. And so there is some evidence, but I think we are still away from, some steps away from the actual proof, I would say. And the proof could be quite non-trivial, actually. And we hope for the best, and in any case, thank you so much. And I think I ran over a little bit. But
yeah, thank you very much, Egon. So please thank Egon for the nice presentation, please, physically or virtually. I'll now stop the recording. Yes, okay, indeed.